So there are all sorts of different types or forms of energy, but I kind of want to get you thinking about energy. And as we talk about energy, kind of get in your mind that just like momentum can be tracked, and momentum won't be destroyed, so also energy can be tracked. And energy generally is not created or destroyed. It didn't come out of nowhere, and it won't go to nowhere, basically. So you might be familiar, I've already kind of been exposed to these terms, some of these terms. If you ever heard about kinetic energy, or KE, okay, that is energy associated with motion, okay. Kind of the yang to that yin would be potential energy, or PE, okay, and that's associated with, oftentimes they call position. It's stored energy. Potential, you have the potential to do something, you have it stored up, you might do it. And down here I've got listed all the different types of energy. There's electrical energy, chemical energy, you know. I have listed here just simply light energy or radiative energy. In Chapter 5 we're going to be talking about a lot of different types of energy related to light called electromagnetic radiation. Just call it EM, electromagnetic radiation. Okay, so that form of energy, although that energy, it's like passing a baton off. If you're like, what are those runners that pass batons off to each other? Okay, multiple runners in the same race. You give the baton to somebody else and they take it. So similarly, energies are like that. Let's see if it'll let me continue to record. Okay, so energy is conserved. So just kind of some pictures here. We see the sun, okay, it looks like the sun, and it is sending what we call radiative energy. And some of that radiation is light, some of that radiation is X-rays, some of that radiation from the sun is gamma rays. We'll be talking about how we're protected from those dangerous energies from the sun. But it sends us energy, and here you see a plant down here, and one thing plants are great at is basically converting radiative energy into potential chemical energy. And here's what I mean. Okay, people will eat the plants, okay, and the only reason they had anything to eat was because of the radiative energy from the sun. And it's all quantifiable, it can be tracked. And so, for instance, up here we see runners. Okay, what are they doing? Well, they ate something. If they didn't eat something, they couldn't, if they starved themselves, they would not be riding bikes like that. So they take biomass that actually was created because of radiative energy, and they consume it, and it is actually converted to energy for their muscles, and then they can make their bikes move. Okay, so they're creating kinetic energy, motion out of biomass, which is potential chemical energy. So kind of along those lines here we have how do we get gasoline? Okay, gasoline actually is a broad group of fossil fuels that ultimately came from organic material, plants and animals living a long time ago. Give it time, give it pressure, and you get fossil fuels. So that actually was radiative energy transfer. It can all be traced back. It's quantifiable. And so, of course, you put the gasoline in your car, and what does your car do? It moves, okay? And motion is a type of kinetic energy. There's all sorts of other things that your car does. For instance, some of that energy, when you burn fossil fuels, is converted to thermal energy. Okay, so it's just a wonderful energy world out there. And energy can be tracked, and it's not created or destroyed. So we say energy is conserved, and I will kind of in the next segment kind of give you kind of a couple exceptions to that. Actually, energy and matter can go back and forth, but for all intents and purposes, we track energy, and energy cannot be created, and it will not be destroyed. But it can change forms, okay, and it can be transferred from one object to another. So basically, at the end of the course, when we talk about the unfolding of our universe, before there was space-time, there was a singularity, okay, and then actually all of the energy and matter that ever was can be tracked. So one type of energy is thermal energy, and thermal energy, remember I said that cars take some of their fuel, and not only do they put it into kinetic energy, but also they turn it into thermal energy. And I maybe want to convince you that thermal energy is actually a type of kinetic energy on the small scale, particles, okay? All matter has motion, okay? I think I'll put that down here. I don't think it's down here. All matter has motion. Okay, and hopefully you can kind of see the motion we have matter here at a cooler temperature on the left and matter here at a warmer temperature on the right. So the arrows are kind of showing you the motion. So something at a cooler temperature has less motion. Can you kind of see the stubbiness of those arrows? And something at a hotter temperature, a warmer temperature, has more motion. So all matter has motion. The cooler it is, the less motion or the slower it moves, okay? Now, if we were to put in a measuring device called a thermometer into each one of those boxes, okay, our thermometer would go up on the scale, and it would tell us, it would give us a temperature for that particular chunk of matter. But temperature in and of itself, whatever our thermometer displays, does not tell the entire story of the thermal energy that those objects contain. I'm going to kind of try to prove that to you. But with regard to temperature scales, if you're like me, I look outside in the morning, or I look on the internet right away and kind of see what the temperatures are going to be for the day, so I know what to wear. And I'm most likely to look at the Fahrenheit scale. It's the English scale. I'm not English. Well, I guess I am, but so the old-fashioned English scale. With regard to that ever-important substance called water, on this scale, water will freeze at 32 degrees Fahrenheit. We keep track of that, don't we? And water will boil at 212 degrees Fahrenheit at normal atmospheric pressures. So then enters the metric scale. So Celsius and kind of the rest of the world, the United States, is gone metric. And actually, when it comes to science, even here in the United States, we definitely, use metric in our sciences, unless you're in, I guess, engineering. I don't know. But so the temperature scale that's metric or a temperature scale that's metric is the Celsius scale. And again, with regard to water, and it's kind of got a nice ring to it, water will freeze at 0 degrees Celsius and water will boil at 100 degrees Celsius. So the number of units between, on the Celsius scale, between which water will freeze and boil, there's 100 units. That's kind of nice. Okay. The last temperature scale I want to show you has, and I'll try to kind of say why we needed to come up with one more metric temperature scale. It actually is the Kelvin scale. Okay. And the Kelvin scale, again, if you look at water, the temperature at which water freezes on the Kelvin scale is 273.15 units Kelvin. Water will boil at 373.15 Kelvin. Now, the difference between the temperature at which it freezes and which it boils, dun, 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 is also 100 units. Okay? So Celsius and metric are both metric. Celsius and Kelvin scale, the Celsius temperature scale and the Kelvin temperature scale are both metric. And so actually 1 unit, 1 unit is the same on both scales. So it's kind of nice. They kind of jump up like this. So the reason they came up, the way I think of it, with another metric scale has to do with this. So I said all matter has motion. All matter has motion, and we said that the energy associated with motion is kinetic energy. So all matter has a certain amount of kinetic energy, and we can use a thermometer to I kind of think of it as you're kind of measuring the pings against that thermometer, okay? So as just like you saw in the boxes a little bit ago, as you slow matter down, okay, its motion slows down. And as you cool matter down, its motion slows. You cool it down even more, its motion slows even more. You cool matter down to a point where it has no motion, okay? That actually is 0 Kelvin, and it's known as absolute zero, okay? So the temperature at which all molecular motion stops is absolute zero. Zero on what scale? On the Kelvin scale. Now, here's kind of the deal. If a premise of matter is that all matter has a certain amount of motion, regardless of how cold it is, and if you have taken matter and now matter has no motion, what have you done? Well, you've basically gone overboard into kind of outside of the purview of what you violated your rule, basically. Okay. So although 0 Kelvin, absolute zero, has been approached, it has not been attained.